Ciao.
Ciao. Aspetta che sono online. Okay, I think we shall start from where we left yesterday. We are going to continue to discuss the step for the modeling procedure with 8 steps. Okay. So today we will discuss very briefly about mathematical formulation, while we will go more in detail into the sensitivity analysis and calibration. These are the 3 central steps of modeling procedure. You will discover that while doing sensitivity analysis and calibration, it is the most time-consuming activities you will do when you are going to build a mathematical model of an environmental systems. Okay, let's go to mathematical formulation. Let's introduce some formalism. We may say that as a definition, a dynamical system can be formally represented by the following ordinary differential equations, are also known as the system specifications. We have a first equation. I hope you can read this notation. This means when we have an underscore, this means this is a vector or a vectorial function or a vector. This is the, and when you have a dot over it, this is the time derivative. So this writing represents the first order time derivative of a state variable vector x. The first equation in the system specifications is a system of differential equation, ordinary differential equation, in which we have the derivatives in times of a state vector variables, or the vector of the state variables, let's say n dimensions. That is a function, again, a vectorial function of the state, of the vector of the state variables, of the vector of the input u, and of the vector of the parameters and of time. So this first writing represents a systems of differential equation, first order differential equation, because we have a first order derivative in times of the vector of state variables. Then we have a second system of equations that defines the vector of E output, that is a p-dimensional vector. This is what you can read from the behavior of your model. So the output, the outcome of the performing of your model will be presented in the vector of the output, epsilon, which is again a vectorial function g of the vector of state variables, of the input vector, and the parameter, and of time. Then we have a set of initial conditions. So we write that vector of the state variable at the first instant of time, so at t0, is equal to the initial values of the state variable. So we are, the third equation is the equation that defines the that defines the starting values of a vector of a state variable. So the first values at time 0 of a vector of a state variables. And then we have a fourth equation, or better, this equality, that represents, these are all, of course, f, g, and h, and all vectorial function. H also is a vectorial function. So this is a system of these equalities that represents the practical limitations or constraints of the state vector variables, or the state variable vectors, and of the parameters. So in these inequalities, we include all the constraints or a practical limitation on the values of the state vector variables. It is here, but you will include information like, for example, energy conservations, or like, for example, the entropy law, so the second law of thermodynamics. So we will write here that the entropy of the system at a certain point is always bigger than, is always increasing, so it's always bigger than the value of the entropy at preceding moments. So you include all the constraints on the state vectors in this inequality. So this is a complete system specification. Please note that equation 1 to 4 depicts a wide range of system behavior in a deterministic way. This is a deterministic description of the system. Please remember, this is a deterministic description. We have all equals or sometimes inequalities that represent limits or constraints onto the state variables. As we have seen, uncertainty is an intrinsic component of every ecological model. So, in order to include some kind of uncertainty or stochasticity, we may use vectors of stochastic processes. Then things get more complicated, but in reality, if we want to describe a real ecosystem with more with a more real approach, more trustful approach, you shall include some kind of stochasticity. Please remember that in general, we employ first order kinetics, so first order derivatives, linear functions, and we tend to be more happy if we can have equations that are independent of time. We have seen autonomous systems. We've seen, we call this autonomous system. Of course, these assumptions are not always satisfactory. So when you deal with complex, complicated real ecosystem, you shall relax some of these assumptions. For example, in some cases, you will use second order kinetics. In some cases, you will use nonlinear functions. Or in some cases, you will have some of the state of differential equations are not autonomous, so they are dependent on time. Of course, you shall be aware of the fact that analytical tractability of nonlinear ordinary differential equation is very limited. And so for not too complex situations, sometimes you may resort to numerical approximation techniques. So this means finding numerically a solution of a system of differential equation. So please note, we would like to be able to have an analytical solution of a system of differential equations, but often this is not possible. So if we do not have an analytical solution, and we will see very soon what I mean by that, we will need to resort to numerical solutions. So this means essentially an important CPU or an important significant computing requirements in order to find a numerical solution of the systems of differential equations. In general, we represent as systems. Remember that the system we are dealing with are bounded systems, so we have a box in order to distinguish an internal constant, if you want an internal stable system or an internal stable part of space, distinguish it from the external unstable and unpredictable. So we have input that are measured, these are observations. Remember the vector of the input, we have indicated it with a UT, vector of the input is a dimensional vector. The input are measured or observations, and then you have, after processing through differential equation, the vector represented by this vector of differential equation xt, by this vector of equation xt, I recall you that this is a vector of state variables, and then we have an output that is what we can observe of the behavior of the system. In general, if we want to include some kind of stochasticity, we may include in our description some kind of stochastic perturbation that will act principally on the value of the state variables. So on the vector of the state variables, we will see some example of this when we will introduce the balance of when we will introduce the transport processes to systems. For example, if we want to describe advection, we do not need to include the stochasticity, while if we want to describe more sophisticated processes that, for example, related to dispersion, then you will include some kind of stochastic perturbation to the system. What are differential equations? Ordinary differential equations may always be recasted in this way. This first equation, f, a function of a state variable, times of a first derivative, second derivative, third derivative of the outputs, and so on, is equal to 0. What I'm doing is I'm simply looking at this equation here, and I'm reversing this equation by expressing one of the vectors or one of the state variables as function of the other, epsilon first, epsilon second, epsilon n, represent with derivative of epsilon from 1 to n. The solution of this ordinary differential equation system is represented by these two equations. We have a general solution, epsilon, the output is equal to a vector function of the state vector of the variables, of the vector of state variables, and then we had the particular solution. You may recall that this is the standard way of finding a solution of a differential equation. You find the general solution, and then you find the particular solution by imposing or by adding some initial conditions. Okay, let's now go into more practical examples to see how, in reality, when we deal with living systems or ecosystem, we may build differential equation model. For example, let's us focus onto a chemostat in which we have a number of bacteria that are growing in time. For example, we may indicate with nt the number of bacteria at time t in steady conditions, and then we know, or we may write that the number of bacteria at time t plus delta t, so successive instance of times, then this will be equal to the number of bacteria at time t plus a quantity that represents the fact that bacteria grows. And please note that here we are in very special condition because we are describing the dynamicity of a population of bacteria, and the quantity of growth of bacteria depends on the number of bacteria themselves times the time interval. So the longer the time and the bigger the number of, the larger the number of bacteria, you will have a greater number of bacteria time t plus delta t. Okay? Why we can write this? We can write this because we are focusing on bacteria. We know that bacteria, when they grow, they essentially duplicate by cellular division. So to each generation interval, we will have a double of n, double of the number of bacteria after cellular subdivision. If we make the time interval dt go to tend to 0, you may recall that this is exactly the definition. You may recall from your mathematical classes on the in high school. This is exactly the definition we limited for delta t that goes to 0 of this quantity is the definition of the derivative, so that if we make delta t go to 0, we have that the derivation, the derivative in time of the number of bacteria is equal to a quantity alpha, the constant alpha, times the number of bacteria at time t. So this is the first order ordinary differential equation describing bacterial growth. And in particular, we may say that alpha, this parameter, it is the intrinsic growth rate or the speed of growth of bacteria. Alpha, it is a characteristic of my bacterial population. Okay? If you don't understand, please stop me. This first order differential equation, maybe we have an analytical solution. The form of the solution, the general form of the solution, let's say that we write a first order differential equation or derivatives in times t of a state variable x. It is equal to a function of time alpha t times x plus a function of time beta t, but is the particular solution. In this case, we know that the general solution is given by this equation, which we have xt is equal to the exponential of the integral of alpha t time the integral of bt time the exponential of the integral of alpha t, again, of alpha t dt, plus a particular solution. In particular, if we assume that bt is equal to 0, the general solution will be this one. And if beta bt is equal to 0 and at is constant, then we have the very well-known solution that is a growing exponential. Nevertheless, it is interesting to note that if you look at this equation, you may ask yourself which is the function of t whose derivative is equal to the function itself. We know from mathematics that the only function whose derivative is equal to its function itself, it is the exponential function. So it is immediate from our basic mathematical knowledge to find the solution of this equation. And the solution of this equation is simply an exponential of a constant k and time t. In general, we may come or arrive to this description by starting also from some other consideration. For example, we may start from including a very general principle, that is the principle of energy conservation, first principle of thermodynamics. In this case, we can write what is called the continuity equations. So we may write that the variation in time of the state variable x is equal to some exogenous terms, so terms due to the surrounding environment. So it is equal to what goes in minus what goes out to the system. So this is really inflow and outflow, plus what? Plus production terms. one is formation, so formation of NTs, or sorry, formation of X's, and transformation of X's in something else. How can we interpret the equation what we have just derived here by employing the continuity equation or the continuity equation or the first principle of thermodynamics, energy conservation? We may write that the variation in time of the number of bacteria NT is equal to the growth rate alpha times the number of bacteria. So we came exactly to this solution. Variation in times of the number of bacteria is the growth rate times the number of bacteria. This is due to the fact that bacteria grows by duplication, so by splitting cells. And then we add a negative term, subtractive term, that we may call mortality. But of course, this is a mortality in a very extensive sense. But is a subtractive term that diminishes the capacity of growing of the bacteria population. By writing the bacterial growth model in this way, and by including, for example, a dependence of the mortality on the number of bacteria, this is how to say, it is as to say that more organisms are there in the batch reactor or in the system, the higher will be the mortality. So the higher will be the competition for resources. In this case, we may rewrite, for example, the mortality as a function of the number of organisms, bacteria, divided by the so-called carrying capacity of a system, so a maximum number of bacteria that the system can hold. And so we rewrite this equation this way, writing that the variation in time of the number of bacteria is equal to R times the number of bacteria times 1 minus number of bacteria divided by the carrying capacity of the system. Then if we redefine, so if we collect NT and we redefine the quantity R with some algebra, we obtain that the intrinsic growth rate is a quantity that is proportional to the distance of the number of organisms in the system from the carrying capacity. When the carrying capacity, when the number of organisms will be equal to the carrying capacity, you will have that the organism growth is 0. The organism stops to grow. Okay? This is very important. It's the first very important way of describing growth, in which we have included not only our knowledge concerning the fact that the growth of this kind of very simple living objects like bacteria is proportional by the number of bacteria itself. That brings us to an exponential decreasing, an increasing exponential solution. But we are also including some kind of limiting or limitation due to the fact that the system that is hosting the population of bacteria has a limited capacity of hosting bacteria, and this limited capacity is described by the carrying capacity quantity N0. So we have a first example of non-linear ordinary differential equation. Ordinary because we have a first order derivatives, first order ordinary differential equation, non-linear because of course we have a dependence here from n and from n square. And this is the very well-known equation of the logistic growth. It is a non-linear equation, and it is very important for historical reasons because it is the first model. It was conceived in the beginning of the 19th century and in the beginning of the 20th century, ending of the 19th century, but described what we today call limited growth. Why limited? Because we have a growing term, positive, to which we add a subtractive term, negative. And in particular, by this description, by including the fact that mortality shall be proportional to the number of bacteria, we end up with a square dependence of on the number of bacteria of the mortality term, the negative subtractive term. So please keep in mind, we will employ this approach all over the rest of the class, of the course. We write a continuity equation by writing that the changing in time of something is equal to what goes in minus what goes out, with inflow minus outflow, plus what it is created and what it is transformed into something else. Creation and transformation may be seen as chemical processes, or may be seen as biological processes. For example, transformation may be seen as consumption. If somebody is eating, then we will have some. If somebody is eating the bacteria, then we will have some of the mass related to the bacteria will be transformed in something else. This very simple first order non-linear differential equation need to be adapted to real systems. And how do we do that? We employ our knowledge about living processes. In particular, a very well-known relationship is that between the length of an organism, so dimension, versus generation time. If we plot length of the organism versus generation time in a log-log plot, then we obtain a linear behavior. We obtain a line whose slope, of course, represent the growth rate. Please note that these relationships are impressive because they span between several orders of magnitude. We go from microns, micrometers, so this means viruses, bacteria, up to tenths, waves, hundreds of meters, oaks or large trees. Again, we span on very large intervals of generation time, going from hours up to hundreds of years, centuries. If we make this kind of analysis of a large number of organisms and we plot a typical dimension of the organism, but maybe the length, for example, but is easy to measure, and another typical measure of the generation time, so the time needed for an offspring to grow, and we put this in a log-log plot, we obtain a very nice linear dependence, what it is called a power law. Please note that you will find several power laws in ecologies, because power laws and ecologists are generally very interested by power laws because when we have power laws, we suspect that there shall be a kind of underlining common behavior or underlining common characteristic in the living process. But even if we do not understand well, or if we do not understand in detail, of course, we can find some kind of relationships, like, for example, in this case, very interesting, nice relationship. These kind of relationships are also very important because it allows you to very quickly switch to dimensions, to timings. So, for example, if you have an indication of the length of a dimension of the organisms, let's say that the dimension of my organism is somewhere here, then you may immediately find that the generation time expected by this organism, by this kind of law, should be. Sorry, yes, please. I made the reverse. Sorry, tell me.
I did not get you well at the beginning of the graph. You say it is the length of what?
The length of the organisms, for example, it might be the size of a bacterial cell, or the length of the linear length of a mammal, or for example, the height of the trees. So you find a linear length quantity describing the dimension of the organism, and you find a relationship that allowed you to pass from, for example, length. You know that organisms whose typical length are on around 1 millimeters are expected to display, sorry, are expected, I'm sorry, but my hand is moving very bad, are expected to display a living or a generation time of 1 day. Okay. These very rough relationships may be found by employing these power laws or with very general relationships that are obtained by classifying and putting on log plots a large number of organisms. For example, here you have a population of bacteria. Uh, Here you have population of, for example, worms. Here you may have population of shrimps, crabs, and then you go to mammals. When you go to trees, you go to oaks, and so on. The impressive fact is that even through the different realm of ecological system, so going from animals to, for example, plants, and from very different animals or different plants, you obtain a linear log-log relationship that may be represented by this kind of plots. This is the typical starting point when you need to identify, for example, first guess of calibration parameters. I do not know where to start for calibrating my model. These kind of relationships that are plenty in literature, that you can find plenty in literature, can give you some guidance in order to identify at least the orders of magnitude of some relevant parameters describing the physiology of the organism. Okay, is that clear? May I continue, Beth? So we have seen that numerical formalisms has to do with finding, for example, the set of ordinary differential equations or the system specification that describes in mathematical terms the object that I want to model. Once I have the system specification, so once I've built up the model, I'm ready to put it in a numerical formalism, and this is the point at which I start studying the behavior of my newborn creature. This is just an example. The example of bacteria is just an example to show you how, with some general consideration on the biology of the organisms, for example, bacteria grow by cellular division, you can build up relationships in time of a number of objects making up my system. Once I have my system formalized in mathematical terms, I'm ready to start to the first important step of the construction of a mathematical model. And this step is called sensitivity analysis. During sensitivity analysis, what you do, you try to identify the most sensitive components of the model. What do we mean by components? Parameters, forcing functions, submodels, and so on. We look for those components of the models that make more significantly vary the state variables. So you look for those parameters, forcing function or submodels, subpart of your description, that make a significant or appreciable change in the value of a state variable. We have a way of measuring these sensitivity, and the way is that of calculating what are called condition numbers. Condition numbers are ratios in which you write that to a corresponding variation of the parameter p normalized by absolute value of P. So this is to a percent variation of the parameter B. P, it corresponds a percent variation of the state variable X. So we have a condition number that represent the sensitivity of my model to the parameter P. You may recall we have seen something analogous yesterday when we were talking about buffer capacity. The sensitivity or the condition number is nothing more than a buffer capacity, a normalized buffer capacity. So you normalize the parameter variation and you normalize the variation of the state variable. So with this ratio, you are comparing how much is varying in percentage the state variable as a consequence of the variation of the parameter P. You understand that this kind of study is very important in order to understand which are the most significant or sensitive parameters or aspects or characteristics of my model. The condition number measures the sensitivity of the variable X to the parameter P. Of course, you have as many condition number as are the combination between state variables and parameters. Here I'm employing the word parameters. Of course, you may do sensitivity analysis also to forcing function or to whole submodels. And this is when you do sensitivity analysis on two submodels, you are essentially accepting that some models that are a sub-portion of your mathematical models may present some kind of emergent behavior or emergent properties that are apparent only when you consider it as a system. So you cannot observe these emergent properties if you split down the system in parts. In general, when we do sensitivity analysis, we investigate at least two levels of variations, for example, plus minus 30% of a parameter, plus minus 60% variation of a parameter. And this step is very important because it is a guidance for the modeler in order to decide which are the parameter to be identified with more accuracy. Of course, most sensitive parameter are the parameter that shall be.
I'm not sure. I already told you. I don't have the phone.
Oh, sorry. Are the parameters that will be identified or calibrated at first. Why we need to do this? This is a fundamental prerequisite in order to proceed with the calibration. Why this? Because if we have a mathematical model that is made up of 50 parameters or even 30, 10, 20 parameters, then it is very, very cumbersome to imagine to change simultaneously 20 parameters in order to calibrate your model. It is much more practical to start calibrating your model by these parameters that are most sensitive, that are the one that make more dramatic changes in the behavior of the model. So by sensitivity analysis, what you obtain a ranking of the different parameters forcing function or submodels from the most sensitive to the least sensitive. And you will start calibration from the most sensitive parameter. Of course, when you do sensitivity analysis, the change applied to the parameter shall be consistent with the uncertainty associated with the parameter itself. This means that it is useless to change a parameter of 1% if your knowledge of a parameter is precise up to 10% or up to 20%. So you will make variations that are consistent with the uncertainty by which you know your parameters. As you know, or as you shall have recognized by now, uncertainty and stochasticity are aspects that are intrinsic to the ecological model. So when you study the sensitivity, you shall start by the assumption that you do not know exactly the parameters. Instead, you know the parameters with a certain uncertainty, so that the variation that you will apply to the parameter shall be consistent with this uncertainty. It is useless to vary, to make a lot of calculations by analyzing the sensitivity of a variation of 1% if your parameter is known with a sensitivity of 50% or 30%. It is also important to notice that the sensitivity varies over time, as we will see soon. This means that as the system, your mathematical model, evolves in time, the various parameters describing the behavior of the model may have a changing effect or changing sensitivity onto the model itself. And then, as I anticipated, you shall take into consideration that it is sometimes useful to make sensitivity analysis also of submodels. In particular, this is very relevant if you have structural changes, for example, new species or new flows or new processes are appearing into a system. So then probably you will have that your submodels in which you are including the new species will be a sensitive submodel. The sensitivity of submodels is also important when you are dealing with conceptual diagrams. So, and I recall you that conceptual diagrams are the starting points in order to identify the right level of complexity of your model. It is important to notice also that some models containing sensitive parameters are sensitive for the main state variables, but it is also important to notice that the reverse, it is not true. So it is not always true that some models that are susceptible to major state variables do not necessarily contain sensitive parameters. Again, being a sensitive part of a model, it is an emergent property. You cannot expect to define the sensitivity by only focusing on some sub-aspect of some models. Instead, you shall define the sensitivity in terms of emergent properties of the submodels. Okay, so it is important, for example, when I'm talking about some model, for example, if I have a eutrophication model, in my eutrophication model, I will have a submodel that we may call algal growth. Of course, algal growth, it is a submodel that is it contains some sensitive parameters that are sensitive to the main state variables. For example, the algal growth rate or the bacterial growth rate. Remember the logistic equation, but nevertheless, the fact that the submodel contains a sensitive parameter does not ensure you that this submodel it is a sensitive submodel. There may be internal mechanism of compensations. For example, when we do sensitivity analysis, let's give a look to classical model. This is a model in which we have phytoplankton, zooplankton, soluble nitrogen, and soluble phosphorus. These are annual average values for sensitivity. So these tables are condition numbers. And these are the outcome of my sensitivity analysis on my model. For example, max growth rate of phytoplankton in terms of condition numbers is quite sensitive to the concentration of zooplankton, because zooplankton is something that feeds on phytoplankton. So the max growth rate of phytoplankton is influenced by these parameters, by, for example, by the concentration of zooplankton. Of course, the max growth rate of phytoplankton is also very sensitive to the concentration of phytoplankton, because we know that phytoplankton are bacteria, unicellular organisms that grow by splitting. So again, the condition number is quite high for the sensitivity of max growth of phytoplankton, for sensitivity of the phytoplankton onto the max growth rate. On the contrary, the one identified in red are parameters that are not sensitive in the model, like for example, the settling rate of detritus displays our condition numbers that are near to zero. So the settling rate of detritus as a parameter is not sensitive to the various state variables, phytoplankton, zooplankton, soluble nitrogen, and so on. Is it clear? This table represents parameters and their sensitivity to, and the sensitivity of state variables, phytoplankton, zooplankton, soluble nitrogen, soluble phosphorus, and so on, to the various parameters. So the first step, in order to understand the behavior of the model, is to calculate sensitivities. So this is called sensitivity analysis. We can do the same by having different representation. In this case, I am employing bar plots by which I am describing. Here we have 1, 2, 3, 4, 5 state variables: dissolved oxygen, chemical, chemical BODs, and chemical and biological oxygen demand, nitrate concentration, ammonia concentration, organic nitrogen. So we have different colors here: violet, reddish, white, and azure. And we see, when we plot condition numbers of the different parameters for the different variables, we immediately see, for example, that the parameter T71, as now I don't remember, I think it is the parameter of the Arrhenius relationship for mineralization. T71 is a very sensitive parameter for ammonia. Again, for example, these are the same analysis to forcing function. These are the sensitivity analysis of the various parameters versus loads, and these are the same versus boundary conditions. This is a very complex model that represents the water quality in the channels of the city of Venice. So we represent the water quality in terms of dissolved oxygen, BOD, ammonia, nitrate, and organic nitrogen, and we analyze all these state variables, how do they change, or how much are they sensible to the parameters in the model. Is it clear? Do you understand why sensitivity analysis is so important? Let's see also that now sensitivity is a function of time. In this plot, for example, we are describing the growth, the biomass of a population that may be a bacterial population, and we are comparing it in terms of sensitivities with the continuous lines are the biomass, and dotted lines are the substrate over which the population is growing. If we make a plot of the value of the sensitivities, for example, we have sensitivities on K, or sensitivity on epsilon, sensitivities on KD. So these are different sensitivities to different parameters. We are plotting these sensitivities versus time, and we are comparing the growth of the population with the decrease of the substrate of the population. And we see that when the substrate of the population comes to very low values, so we are in the limit in which the population cannot grow anymore, then you will have a negative effect on the sensitivity on the growth rate of the population. So even if in the beginning the sensitivity of growth rate parameter mu is almost zero, while the substrate is consumed, during substrate consumption, you will have an increase of the sensitivity of the population of the parameter growth rate, because of course growth rate is dramatically influenced by the presence of a substrate. Same thing, you can make the same analysis here. Here we have biomass and related sensitive. So these are sensitive to substrates, and these are sensitive to the biomasses. So here we are analyzing the sensitivity to the parameters of the substrate. Here instead we are analyzing the sensitivity to the parameter of the biomass. Of course, the substrate and the biomass are state variables. The quantity of food is the substrate, and the biomass is the quantity of organisms. Again, we see that when the organisms stop growing, so after this point, we have a first significant consumption of the substrate, and then the sensitivity dramatically drops to zero with time. Okay, so please remember that when you are going to do a sensitivity analysis onto your model, it is also important to verify and study, analyze the effect of the sensitivity along time, because sensitivity is a quantity that describes time by time, every instant, the sensitivity of your model, and this characteristic of the model may change with the changing of time. Okay, once we have made sensitivity analysis, so we have a nice ranking of the parameters from the most sensitive to the least sensitive, when you're ready to start with calibration. What is calibration? Calibration means estimating the ecological parameters, estimating the value of ecological parameter. In general, these parameters do not have exact values because the model is a simplification. So when the value of a parameter you include into your model do not are consistent with the same parameter that you measure in real experiments, this is probably due to the fact that the model is a simplification of a reality. So the parameter in your model is not playing the same role of a parameter in the real system. Then you have to take into consideration when you may have aggregated parameter models. So into your single parameter, you may include the spatial variability, but also you shall take into consideration that ecosystems or ecological systems are flexible. So they are able to display structural dynamicities. That means the systems are able to change their structure according to the changing of the surrounding conditions. Please note that we may say that parameters are sensitive or affected by environmental factors, of course. These quantities are iterative and subject to feedbacks. So it may happen that you may determine very well a first parameter when you pass and calibrate the second parameter. And when you discover that your first parameter calibration was not adequate anymore, so you have to go back to calibrate the first parameter. And then you have to keep in mind that the parameter can be determined indirectly parametric, for example, by allometric relationships like the one we have seen between the length and the growth and the generation time of the animal. Or you also may use your knowledge about reaction time, chemical composition, or energy content in order to have a first guess of a parameter. So to find parameters value, you give a first guess from the literature. Typically, I will give you soon an example of the handbook of ecological parameters by Sven-Erik Jorgensen, in which you have a list of parameters and the value of these parameters with the reference of the papers in which these values were used, so that you can compare the papers, you can study the papers and find, for example, systems that are quite similar to yours, so that you have a first starting point to introducing first values of the parameters. So you start with the first guess from literature, a handbook of ecological parameters. You can make in situ process analysis, for example, respiration analysis, or energy consumption, or excretion analysis. You can conceive additional experimental measurements in order to determine more exactly those parameters that are more sensitive. You have to verify that the time is appropriate to capture the variability of a system. What does this mean? This means that your model timing shall be enough resolution, high resolution, in order to follow the variation of the state variables that you are focusing on. If your model is only giving you average values, then it is useless but to try to calibrate your model with these parameters that describes only averaged conditions. This is an extract from the handbook of ecological parameters by Sven-Erik Jorgensen. For example, for different algal type, phytoplankton, total, diatoms, green algae, blueing, and so on, you have values, interval values of a parameter, in this case the settling velocity. And for example, you may find that for diatoms, Biermann in 1976 employed a value in the range 0.05 to 0.4 settling velocity, what is meter per day for diatoms. So you see this parameter depends on the type of organism and on the particular ecosystems you study. So if you make a crossing between the type of organism and the literature in which it is described the ecosystem, then you can find you have a guidance in selecting appropriate guess estimates for parameters. Okay, let's, for example, give another example. Let's give another example of a group model. In this case, we have started the lecture by introducing a model for bacterial growth, and we ended up with the with the logistic flow model. For example, we may start again by for a general organism without specifying if it is a bacteria. Let's, for example, focus on fish growth. You may write that with growth of a fish, of increase in mass, that is generally called anabolism, is equal to the variation in time of the weight of the organism's growth, and may be explicitly by a continuity equation, so that is by an application of first principle of thermodynamic energy conservation, we may write that the anabolism, the growth of the organism, is equal to the metabolism minus catabolism. The metabolism is the quantity of energy used per unit time, unit volume of an organism during its lifetime, whilst catabolism is the quantity of energy used per unit time per unit volume just to maintain a surviving organism. So metabolism is given by the sum of anabolism growth plus catabolism, the energy employed to stay alive, which is a very trivial way of translating the principle of energy conservation. For example, I may describe the organisms, my system, again, a box with boundaries in which I have food that is entering into the body of the organism, and then food, but with food that is transformed into energy by digestive processes, is then the energy produced by this form is then employed for respiration, for some part of the food is non-digested and yes, some part is assimilated, so this is a real growth, anabolism, and some is non-utilized, so it is excreted, directly excreted and non-processed. So we may write that variation in time of the weight of a fish is equal to a constant 8 times a function of the weight of a fish. This is non-linear, of course, because we are making the derivative, first order derivative of weight dependent on an exponential power, a beef power of the weight itself. The energy obtained by digestions may be calculated, for example, in terms of, we have that 9 parts of the energy depends from the content in fat of the food, and 4 parts of the energy depends from the percent content of the food in carbohydrates and protein. So by this you can calculate the energy. This is a way of putting numbers on these arrows. By writing this model, and if we go to a log-log representation, of course, you may realize that if you make a log-log representation here, the exponent goes down, the logarithm, so that your model is transformed this way. So you may write that metabolism, so the total energy employed by the organism, is equal to what is employed for growing, the u, the t, the derivative in time of weight, plus the energy employed for living, for being surviving organism. This second part is a function of the weight, in particular the function of the weight we have seen here is b power of the weight, so in exponent b exponent, the weight elevated to an exponent b. Again, in log-log relationships, we find several allometric relationships that link, for example, the weight of the organism versus the metabolic rate. You remember we have introduced the first allometric relationship linking the length of the organism with the age, so with generation time. Here we have a similar relationship in which we have a linear log-log relationship between the weight of the organisms and the metabolic rate, so the calorie consumed by unit mass, unit time, calorie per gram of organism per hour or per time. If you put on a log-log plot this, you obtain, but for example, again, very different organisms, in particular for unicellular bacteria, you obtain this first row, this first line, while for heterotherms, you obtain the second line, and homeotherms, you obtain this third line. What is the difference between heterotherms and homeotherms? Heterotherms are organisms who are not able to control the temperature, so are organisms whose temperature is dramatically influenced by the temperature of the surrounding environment. Instead, homeotherms are organisms that are able to maintain a stable temperature, like, for example, are mammals. So, if you fix, for example, the weight of your organisms, let's see if I'm able to make a simple line. If you fix the weight of an organism, let's say my organism weighs 2 grams, then of course I will have that for heterotherms, the metabolic rate is this one, while for homeotherms, the metabolic rate will be this one. So it is not surprising that for organisms that are able to maintain stability in temperature, they will consume, in terms of metabolism, more energy per unit time, unit volume of the organism. Again, this kind of anometric relationships are very useful in order to start identifying the values of the parameters of organism, especially if you do not know in detail the organisms, but for example, you just know some characteristics of this, like for example, a dimension or an energy consumption. You have several anometric relationships for many other quantities or substances that are of relevance, for example, for the environmental engineering. In particular, this plot is showing concentration factors for cadmium versus size. And again, you see that for very different fish like goldfish, mussels, shrimps, zooplankton, algae, for very different organisms, you have that the concentration factor for cadmium disposed in a log-log line on a linear disposition. Okay, again, we have here a relationship linking a dimension of the organisms, for example, is the size, with the concentration factor. You may recall concentration factors are the key parameter in ecotoxicological models. The concentration factor is the ratio between the concentration of a chemical into an organism divided, for example, by the concentration of the chemical into water. So this is bioconcentration factors. Bioconcentration factors are linked to sizes like this one. So with an anometric relationship, not only we have another one here, in particular, this is a process uptake rate of cadmium that is plotted against the length of various animals. In particular, you have 1 for phytoplankton, 2 clams, and 3 for oysters. Again, you have a linear relationship in log-log, in which you have an uptake as a function of length. Again, this type of relationships are very useful when you're dealing with calibration, like for example, if you have one parameter that describes the uptake of the organisms. Uptake means how and what the organism eats, and you can start by this kind of plots by making some kind of inferences by starting from your knowledge of the organism that you're studying. For example, a 1 millimeter organism, I'm expecting that this displays a factor of uptake between 10 and 100 in logarithmic scale. Again, this is the same for DDT and PCBs. So this is just to say that in literature, you may find plenty of this kind of relationships that may help the ecological modeler in calibrating or finding the first estimation of the model, of the parameters of your model. Of course, this is a first guesstimate when your procedure for calibration may employ more sophisticated approaches. In particular, we will finish the lecture of today by giving you a list of most general evaluation methodologies for the behavior of a model. So given that the objective of a model is to being able of reproducing reality, so what we are looking at the calculated state variables are observed, calculated values of state variables shall be the most similar as possible to those observed in nature that are measured. So what I'm looking for when I'm doing calibration is that I would like that the calculated values of state variables are consistent, close to the measured values of the same state variable. There are many methods for assessing the goodness of a model. We may identify here three general categories: visual techniques, or measurements of deviations, or statistical tests. For example, in the case of visual techniques, I can show you an example. This comes from the Mces application, modeling nutrient emission to river system. Here we have, as a function, we are observing a river, large river, a poor river, that is 1,500 cubic meters per second discharge the river in northern Italy. So it is a very large river. We have employed a model for estimating concentration of phosphorus and nitrogen. In particular, we may go along the river. So this is the distance from the spring, and we may observe at different distances from the springs, we have these measured values. So what I've been doing for calibrating this model, I've been acting on two parameters in order to move this pink line the most closest and most consistent to measured or observed values, to the dots. You can do the same. This is the same model here beneath, which instead of employing only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, these points are all along, these gold points are all along the main river flow. Instead, these crosses here are calculated into the sub-basin clusters of the poor river catchment. Okay, I know this sounds to you very cloudy, but when we will introduce next week the Mces model, this will become evident to you. The point is that if we look and we check the consistency between this is dissolved in organic nitrogen load that is measured by sampling the river. And this is the dissolved in organic nitrogen load as calculated by my model, where units are tons per year. And if we make a comparison of these values, measured toward the calculated one, I would like that these values are displayed on the one-to-one line. Of course, this is not always the case because here we have 33 sub-basins. So for each of the sub-basins, you have a certain displacement from the one-to-one line. The reddish line are the plus 30, minus 30% of this displacement from the one-to-one line. What you observe is for example, dissolved in organic nitrogen increases into the catchment, you will have that the values will tend more and more toward the one-to-one line. So that for the largest basins, so for those who most contribute to dissolving organic nitrogen, I am committing a smaller error by application of this model. Why this? Because as the catchment, the subcatchment grows in dimensions, you will have uncertainties in plus direction and uncertainties in minus direction. So uncertainty in growing and in decreasing that compensate each other, so that when going toward bigger and bigger subcatchment, the error of your model tends to decrease. So this way of analyzing graphically or visually data is a first approach in order to modify the behavior of your model so that all the crosses tends to a one-to-one line. So this is a visual technique that helps you in changing the values of the parameters in order to make the behavior of the model the most as possible adherent to the reality, to the observed data. Of course, these are only one example, but there are also several automatic algorithms that works together, that works on the whole space of the parameters in order to change them and finding the minimum of some measure of the distance from the plot, from the output of your model and the observed data. Here we have again, this is dissolved in organic nitrogen. Why here we add total phosphorus? Here we have dissolved in organic nitrogen. Again, the model is acceptably calibrated if we obtain a pink line like this one, and this is total phosphorus along the main river. There are automatic algorithms, for example, the method of the simplex, that changes the values of the parameters so that this curve moves in the space of a solution and finds the best set of parameters in order to reduce collectively the distance of your solution from the observed values. Then there are measurement of deviations, of course, like for example, a mean absolute error, and I'm presenting here the definition of mean absolute error. Mean absolute percent error, so it's the same thing, but it is normalizing to a percent. The root mean square, so these are collective measures of distances of simulated values from the observed values. In particular, this epsilon with a tilde on it is simulated values. Epsilon is the observed values, so measured, and epsilon with this underline the average of observed values. Root mean square is given by the square of the difference between observed values and simulated values divided by the number of observed values by the number of points. These are very statistically robust way of measuring the distance. Statistical tests that are customarily employed are, for example, the t-test, that is used for independent data, so data for which we have unknown variance. The chi-square testing that is instead employed for correlated data for which it is known the variance, but by far the most useful and employed test of performance of your model is the efficiency indicator. The efficiency indicator is defined as 1 minus the ratio between the summation between the differences between observed and calculated data, and the difference normalized by the difference by observed and the average of observed data. What does this quantity tells you? I am expecting values of efficiency that are lower than 1. If I have negative efficiencies, this means that the denominator part of this ratio is bigger than the numerator part. So this means that if you are employing the average of the observed value as your model, you will commit an error that is smaller than that of applying your model that gives as a result epsilon tilde results. So the idea is that I calculate the efficiency. The efficiency is 1 for a perfect model, because we have 0 differences between simulated and observed data. The efficiency is negative if my model performs better than the average. Of course, the average is another model, but the average is the best value approximating all the data that I am observing. Okay, so by far, the most employed test of efficiency in ecological modeling is the Nash and Sutcliffe coefficient, or the coefficient that I have defined here. Okay, if you don't mind, I would like to stop here today. Do you have any questions?